Okay, so this is Unit 8, Day 2, and we are working out of pages 5 and 6 in the note packet, and you have these two con to do after you get done with this lecture. So today we're going back and talking about motion, and we're going to relate it to integration. So we've talked about motion before. We've talked about position, velocity, and acceleration and how they were related back in first semester. So today's focus now is how do integrals explain the characteristics of motion. First semester, we had how does derivatives explain the characteristics of motion. So this is very closely related to that. So this is kind of a review of the relationships between position, velocity, and acceleration, okay, that we learned first semester. So for instance, if we started with our position function, if we started with that, we would differentiate that or take the derivative to get our velocity function. And once we had our velocity function, we could differentiate or take the derivative again and get our acceleration function. So that was the process for last semester. This semester, since we're working with antiderivatives, we're going to be working in the opposite direction. So we're going to be starting with acceleration, and then we're going to take the antiderivative of that. And you remember, we got to kind of combine two concepts here, the fact that we're doing an antiderivative and these first semester relationships. But when we take an antiderivative, you also have to remember that antidifferentiation represents a change in a value. So taking the antiderivative of acceleration will actually get us a change in velocity. Okay, and then we can go and take the antiderivative of velocity, and that represents a change in position. We call that displacement. So that's what we're going to focus on today. Is relating the motion concepts to the antiderivative or to the integration in that way. So we now that we've reviewed what we did first semester and how we're going to reverse that process for now, we also have to review the idea of integration or taking the antiderivative. So I'm just going to kind of refresh your memory with this activity we did earlier this semester, and this is one of our anchor charts. Right, we had a function. This was f of t equals 2t, and so we need to talk about what happens when we integrate here. So when we talked about this and made this anchor chart as a class, we learned about the definite integral and how it represents a change in a value. So for instance, and this is really foundational to understanding this section. Okay. This is kind of the building blocks here. So in other words, we started out by saying, hey, what's the integral from 2 to 7 of little f of t, right? And we know that little f of t is our derivative or our rate. And so we said, well, hey, we can just color in the area underneath that function. And we know that the integral then is 45. And so that 45 represents a change in a value. It represents a change in the antiderivative value, big F. So what this 45 represents is, since we went from 2 to 7, it represents the value of the function at 7, big F. So that value at 7 is 49, minus the value of the function at big F at 2, where we began, which is 4. So if we notice, when we integrate, or when we find the area under the curve, we get 45. If we take the difference of the two antiderivative values, the big F's, 49 minus 4 is also 45. So that's why we say that integration represents a change in a value. Integrating the little f, the rate, represents a change in the antiderivative value. And we said, well, and so this was so important, we gave it its own theorem, and that's the fundamental of theorem of calculus part 1. So that's why we say that this is foundational to understanding this section. We're really going to rely on that fundamental theorem of calculus part 1. So if we apply this to motion, we talk about a change in a value. We can talk about the change in one of these two values. We can talk about displacement, which is a change in position, or we can talk about a change in velocity, which doesn't have any special name. We just call it the change in velocity. Let's talk about displacement first. So displacement would be integrating the velocity function. So if we integrate the velocity, that's the rate of displacement, that's the rate of change of position. If we integrate the velocity from A to B, then that is equal to the change in the position value. So it's the difference between the position at point B and the position at point A. So this integration represents a change in the antiderivative value. Okay, we typically call that displacement. We could also call that change in position. Okay, and we don't use the change in velocity expression as much, but we will use it from time to time. And I have an example of that in today's lecture as well. So to get a change in velocity, we're going to have to integrate the acceleration, because acceleration is velocity's rate. So we have to integrate the acceleration function between two time periods. And so that's going to be equal to the velocity at point B minus the velocity at point A. In other words, this is the change in velocity here. How much has the velocity changed from point B to point A? So we're going to look at that, not as much, but we'll need that. It's more of a stepping stone as we focus on displacement. So to look at more formal definitions for motion in the way it kind of is referenced in this section. Oh, it looks like I have a typo there. Let's first talk about displacement. So we know displacement is a change in position, and so what we often do is we refer to displacement as the no, that's out of order. Don't pay attention to that right now. We refer to displacement as the integral from A to B of the velocity function. And that represents our change in our position, the change in the antiderivative value, which is position. So if we look at this velocity function here, this velocity function is trigonometric with some other stuff added in. And so if we think about the displacement here as being the integral from A to B, so let's say we started at 0 and we went out to 1, 2, 3, 4, we went out to 5, then these regions between the function and the axis, so between the function and the axis, would be a negative region here, and a positive region here, and a negative region here. Those all represent displacements during the certain time intervals. This one looks like it's from 0 to about 2. This one looks like it's from 2 to something a little bit bigger than 3. And since I know it's a trig function, I'm going to guess this is probably pi. And then we also have a region here from, I'm going to call it pi, all the way out to 5. I'm just guessing it's pi because I know it's a trig function, and that seems to make sense to me. So let's take a look at this then. We can figure this out graphically. That's the way we have our information. So if we want our displacement, I'm going to integrate the velocity function, and this is the velocity function, t minus 2 sine t. So if we think about these zeros right here, what makes the velocity 0? What values of t? 2 does, because 2 minus 2 is 0, so this has got to be 2. And what makes this 0? Pi makes this 0. So yeah, this is definitely a pi here. So we're going to integrate this from 0 to 5. And all that means is we're going to tally up these regions and what their areas are, what their values are. And so this would be a good example to pull out your calculator and do a Math 9, and just to see what you get instead of doing the integration by hand. Because this integration by hand would be really complicated. It's beyond the scope of this course. So when I pull out my calculator and I do an F9, I do an F9 between 0 and 2, and I get this value. And then I do an F9 between 2 and pi, so I change this from 2 to pi, and I get this value. And then I do an F9 from pi to 5, so pi to 5, and I get this value. So I know then my displacement is going to be whatever those things add up to be. So when I add up those regions, and I'm using the word add loosely because we have negative values in here, so adding a negative would be the same as subtracting. I get an overall displacement of negative 3.811. So what that means is that wherever I started from, by the time I get done with this 5 seconds of movement, I am 3.811 meters to the left. That's what the negative sign means, to the left of wherever I started. So if I started at 0, I'm at negative 3.811 on the number line. Does that make sense? If I started at 10, then I'm at like 6.189. I think I'm subtracting that correctly on the number line. So that's the first formal definition here. Displacement is integrating the velocity function. We can also find the total distance traveled. Now, total distance traveled is slightly different than displacement. While displacement takes into consideration positive and negative movements, like positive and negative regions, total distance takes all of these movements and considers them positive. It's kind of like your odometer on your car, right? If you drive to school, you tack on maybe 2 or 3 miles, but then when you drive home, since you're going in the opposite direction, your odometer doesn't take off those 2 or 3 miles. That would be kind of nice. But instead, your odometer adds 2 or 3 more miles, even though you're traveling, quote unquote, backwards or in the opposite direction. So total distance travel is your odometer. And so it takes all of these regions and considers it positive. So the really cool thing is if we were to do this on Math 9 on our calculator, all we would do is grab the absolute value function, and that's under the math key. And we would do the Math 9 to get the integral. We'd stick in 0 to 5. So let's get this function up here. We'd do our Math 9, stick in 0 to 5, go back to the math function, get our absolute value, and then type in our function, of course, making sure we're in radian mode. And then it will just give you a flat out answer. And the answer it's calculating is doing this. Watch the animation here. The calculator is thinking of all these things while it's doing this absolute value. The first thing is it's looking at this first region here. See my flashing dots? It's looking at that first region. And it's saying, hey, this is a negative region, but I need my total distance. So I'm going to make that positive, and I'm going to give it its positive value that's the same as the negative value. And then it looks at the next region, and it says, well, that's already positive, so we're good with that. And then it looks at the last region and goes through the same thing. It says, hey, that's negative, I'm going to make it positive, and then it adds up all those positive regions. And so our total distance traveled, like traveling to and from school, would be just adding up all of those little trips, so to speak. So our total distance traveled here would be 4.275 meters, and that accounts for all the back and forth we might do. So that's another thing they could ask you. The nice thing is it's really nice when we use a Math 9 on our calculator, because all we have to do is the absolute value. If we need to do this by hand, it's a little more cumbersome, and we'll get into that in the next section, where we have to split these up, so we have to find these zeros. But I kind of alluded to that when I talked about this, right? The zeros here are 2 and pi, because it's setting the velocity function equal to 0. And then we would have 3 integrations to do. Okay, so before we go any further with the information on this page, I just want to stop and talk a little bit about the total distance traveled. When we're talking about that total distance, we need to make sure that that function is always positive. In other words, it's always up above the x-axis here. And so you won't have space for this in your notes, so this is more just kind of a general discussion. But if we look at the total distance traveled, we know that's a question that's answering how far have we gone. So we talk about the odometer reading always being that total distance, that how far. And really, it's if you got a calculator, a Math 9, using the absolute value is the best way to get that answer. However, there are times when they ask this question, how far, and they don't let you use a calculator. And what they're doing is they're just playing a little bit of a trick with you on functions. So let's take a look at this function. This function is e to the x. So if I'm asking you how far we've traveled, and we start at like time t equals 0 and go out to t equals 3, it would be this whole region underneath the curve. But if you notice, this curve is all positive anyway. So any accumulation will be up here in the first quadrant. So when we're talking about an exponential function, we can always just drop the absolute value and just do a regular integration. So whenever you're dealing with exponential functions, a Math 9 is obviously the easiest way to go, but sometimes they will give you a question that they won't allow you to use a calculator on. And when they do that, it's because they know that you can just integrate this regularly, because it will always be a positive function. So we can kind of extend that to other functions too. For instance, here's a x squared. So if we integrate an x squared or a t squared again, even if we were to integrate it for negative values of x and positive values of x, this region would always be positive. So we can just drop the absolute value signs and do a regular integration by hand. Another function that behaves the same way as this function, that's the square root. So again, always positive. It's not crossing the horizontal axis at all. We can just drop those absolute value signs, convert that to a t to the half power, and do our regular integration. And then they might give you something like this. Now this looks a lot like the function above, where it goes above, dips below, etc. And so if we were to ask you, from 0 to 6 to calculate how far, definitely the Math 9 key is the way to go. But there is a region where this is positive, and that's from 0 to pi. So this is this is a sine function. So if we just go from 0 to pi, the sine function is always positive. So we have to watch our domain here, but we know that when we integrate from 0 to pi, since if the function is always positive, we can drop the absolute value signs. And the same thing is true for the cosine function. We just have to watch that domain. If we integrate from 0 to pi over 2, again, this cosine function is always positive. So we can drop the absolute value signs and do a regular integration. So that's the way they get around using the Math 9 key, and can put some questions like this in the no calculator part. So for total distance traveled, for that how far component, Math 9 is definitely the easiest way to go, but we can do regular integration if the function is positive or greater than 0. So what I really want you to get down is, in your notes here, is this comment that total distance is how far, and the comments below the box here. The Math 9 key that you should be using if you have a calculator, or making sure that if you're doing regular integration, in order to drop these absolute value signs, you have to be integrating a function that's always positive. So as you can see, this is really heavy in the fundamental theorem of calculus part 1. So it's really dependent upon taking the integration of the rate, or the little f as we would call it, and equating that and making that equal to the difference of the antiderivative functions. So as we always say, that definite integral represents a change in value. And that's exactly what the fundamental theorem of calculus is saying. The definite integral represents a change in the antiderivative value. So we can rearrange this then, and we did this in the last unit to find a final position. We call these initial condition problems the last unit. In other words, if we want to find our final position, that would be this right here, big F of B. If we wanted to find that, all we have to do is take big F of A to the left side of this expression. So we're going to add it to the left side. So it's going to look something like this. Now, my final position, S of B, is going to be integrating my velocity function from A to B, plus adding on wherever my position was at A. And so we're going to use this, we're going to rely on this a lot to find final positions, but it really is nothing more than applying the fundamental theorem of calculus. And we did this back in the previous unit when we were working on initial condition. Here's our first example. So we have a particle that moves in a straight line with velocity v of t in meters per second. So here is the velocity function for this particle, where t is in seconds. At t equals 3, the particle's distance from the starting point was 4 meters. So when we get to this point in time, we know we're 4 meters, we're basically at +4 on the number line, okay? And then it says, what is the particle's position at 8? So after we go from 3 to 8, what is the particle's position? So what we need is the displacement here from 3 to 8, so that we can figure out how much the particle moved. So we're going to really rely on this expression here. Our final position is equal to the integral of our velocity function between our initial and our final point. Initial point is A, final point is B, plus our initial position at time A. And so we're going to modify that to fit this problem in this fashion. We know that we are starting at time t equals 3. So that's our A. And we know that our position, our big F, so to speak, I called it big S here. Our initial position is 4 meters. That's our S of A. And then what we're being asked to find is where we are, what is our position, our S of B at 8 seconds. So that's got to be our B. So adjusting the expression here for this problem would look like S of 8, that's our final time, equals the integral from 3 to 8 of the velocity function, plus our position at 3 seconds, our S of 3, which happens to be 4. Okay, so now we have to figure out how we're going to integrate V of t. In this case, we have a graphical representation of our velocity. So we're going to just go ahead and do our area calculations. So the region from 3 to 8 looks to be all positive. So we're going to look at this region here, which happens to be 2 triangles. So we have half base times height. Half, the base is 3, the height is 5. Plus this other little triangle, which is half base times height. Base is 2, height is 1. So this is 7.5, and this is 1. So we have 8.5 in displacement, and then we have to add on our initial position 4. So our final position is at 12.5. So that's one way of adapting our fundamental theorem of calculus, part 1, to fit our motion problems. This next example has a particle moving along the x-axis. And we're looking at positive values of time, which should make good sense there. We don't have anything such as negative time. We have an acceleration function. And then we have a bunch of conditions that we have to meet. Okay, we say the velocity at t equals 0, the velocity starts out at 7. And its position at t equals 0 starts out at 0. So right on the origin there. So we want to find its position at time t in general. In other words, we want to find the position function. And so this is one of those occasional instances where we have to use that velocity expression too. So we have to adopt the fundamental theorem of calculus to take us from an acceleration function all the way to a position function. And that's going to require 2 integration steps. So we got to start out with integration. And if you remember back to that first slide in this lecture today, we're working backwards through those motion concepts. So what we're doing is we're going to use this and we're going to modify it slightly. We're going to get our final function. I guess we could almost say final function by taking this and modifying it slightly. So instead of having its specific ending point, we're going to have a general ending point t. And we are going to get rid of the upper and lower bounds. We're just going to do an antiderivative here because we know this represents a change in a value. And then we're going to add on the initial condition, which is just finding that plus c. When we do an antiderivative, we don't have to tack on a plus c there. So we're going to have to find that constant of integration. So that is what we're going to work with. And now we have to adapt it for this problem in particular. We can't find position right away because we don't have velocity. So we're going to have to find velocity first by a velocity function by integrating acceleration. If you remember going back to that first screen on our lecture here. So we are going to integrate acceleration. That's our acceleration function, minus 4 sine 2t. I'm going to drop off the plus c for a second. Let's just do this antiderivative. So the antiderivative is 4 cosine 2t. Right? The antiderivative of minus sine is cosine, or the antiderivative of sine is minus cosine, and we have minus and negative, which is a positive. But then we have a chain rule. They love to sneak the chain rule in here into trig and into e functions, exponentials. They love sticking in that chain rule. So we know we have to divide by the derivative here. That's our antiderivative process. We have to divide by 2. Now we can put on our plus c. And now we can go to this initial condition up here. So let's clean this up first. 4 divided by 2 is 2. So our velocity function is 2 cosine 2t plus c. Now let's look at this initial condition up here. When t is 0, the velocity at time 0 is 7. So we're going to put that information in here. Our velocity is 7. And that occurs when we have a t of 0 and 2 times 0 is 0. Now we can find our c. So cosine of 0 is 1. So this is 7 equals 2 plus c. So c must equal 5. So our velocity function then looks like this. It's 2 cosine 2t plus 5. So that's our velocity function. So we're halfway there. We're halfway there, and we still have to integrate this to get our position function, right? That's the relationship between velocity and position, and that's what it's asking for. But let's just take a pause here, because this is a multiple choice question, and you can start perusing the answers, and you can start making some pretty educated guesses at this point. If this were a test, you might want to stop and look at the answers and say, hey, can I rule out any answers? Or can I nail this answer even without doing the second half of the problem? And I would say you definitely can nail this answer without doing any more work. We know we're going to have to integrate velocity, so we know this is going to go to a sign. And we have a 5 in the picture, and that's not going to change. And when we integrate that, it's going to be a 5t. So I think we can really clearly see what the answer is already. But let's just go through the second half of the problem just to convince ourselves. That's a good time-saving technique, but really, let's kind of treat this as a free response problem where we don't know the answer. So now we have this. And let me just back up. Well, let's not back up. This next step then is to integrate the velocity function. So we know the velocity function is 2 cosine 2t plus 5. And we're going to integrate that to get our position function. So the antiderivative of cosine is sine. So we're going to have 2 sine 2t divided by 2 because we have that pesky chain rule again. So you can kind of see the patterns here, right? When we're dealing with trig functions, we're going to go from sine to cosine to sine to cosine to sine to cosine to sine to cosine. When we have a pesky little chain rule here, we're going to keep dividing by the derivative, dividing by the derivative, dividing by the derivative. That helps these coefficients go away. That's kind of nice. Same with exponential functions. Same sort of pattern you're going to see, right? Integrating exponential functions is itself, and then we're going to divide by whatever derivative we have in that chain rule. Anyway, back to this question. We still have to do the antiderivative 5, which is 5t. Now we can put on our plus c. We can clean this up. 2 divided by 2 can cancel those things out. So here's our position function. And now we can pay attention to our initial position here. So our initial position at time t equals 0, we're going back to the beginning. Our position when t is equal to 0 is 0. We start right at the origin. So we're going to put in those values here. Our final position is 0. When our time is 0, and we still have another place where we have to put in a 0 because we have a t there. Now we can find our c. Sine of 0 is 0, so this whole thing is 0. So that means we don't need the constant of integration because it's 0. So our position function is that, and as you notice, that is the answer we were kind of thinking about on the previous screen. Okay, so that pretty much covers it. It's, like I said, this section is really heavy on applying the fundamental theorem of calculus part 1 and kind of tweaking that to suit your needs. Sometimes you can just plug in initial and final values and get a numeric answer right away. We call those initial value problems. We did those in our last unit with differential equations. And this is more of the same. And then sometimes we need to find a function. So we start to drop the upper and the lower bounds, and we need to put that plus c on that we need to find. So that's like finding a particular solution, if you remember that back in differential equations. That's what that process is. So back to our essential question, how do integrals explain characteristics of motion? We know that integrals represents a change in the antiderivative value. And that's why it's so closely related to the fundamental theorem of calculus part 1. So the homework for tonight then is these two cons that deal with motion problems, and you'll have an opportunity to do both of those types of problems.